The second talk of the morning session is given by Rita Pardini from Pisa, and she will explore the boundary of the Moduli spaces of speakers of the data.
Thank you. And first of all, I'd like to thank the organizers for this invitation. I'm enjoying the conference in Florida very much. It's my first time. And I'm going to talk about joint work in different combinations with different people. So I even have abbreviations. So we have Stephen Coughlan, Franciosi, Rana, and Rollenske. And all the talk will be about complex varieties, and when I talk about surfaces, I mean projective surfaces. So let me just try to give you some context, some setup. So you fix two positive integers, A and B, and then there is a coarse moduli space, MAB, constructed by Gieseker, I think at the end of the 70s. And this parameterizes surfaces of general type with Kx sample and at most canonical singularities, and with the given invariance. K square is equal to A, and chi is equal to B. And then later on, this was extended to the so-called KSBA, Collar Shafarevich moduli space. And this parameterizes stable surfaces with the same invariance. I'm going to say what stable is in a second. But the Gieseker's moduli space is contained in the KSBA moduli space. And the Gieseker moduli space is a quasi-projective variety, while the KSBA moduli space is projective. So we talk about a compactification. The situation is similar to that you certainly know very well for curves. You have moduli of curves, which is a quasi-projective, and then there's a compactification obtained by adding these stable curves. The difference is that as soon as the dimension goes from 1 to 2, even the Gieseker moduli space is largely unknown, and the stable surfaces, the objects that you have to compactify in order to have a projective variety, are much more complicated. That's what the exploring in the title referred to. The aim of this work was to try to understand in some concrete examples what the surfaces actually occurring at the boundary of this moduli space look like. And yes, two cautions if you are used to moduli of curves. We talk about compactification, but the Gieseker moduli space is open inside the KSBA moduli space, but it may not be dense. Actually, most of the time it isn't dense. And then the definition here is less obvious, because moduli space are not only about varieties we want to classify, but what families are. And in the construction of the KSBA moduli spaces, you consider Q-Gorenstein families, which means you have flat families such that the total space is Q-Gorenstein, namely the canonical class of the total space is Q-Cartier. So let's get to what a stable surface is. I'm not going to give you too many details. So Kx, the canonical class is Cartier, and X has semi-log canonical singularities, and I forgot the most important condition that's good about this way of giving talks is Q Cartier and ample. So, and the second condition is about the type of singularities we admit. And I'm not with so-called semi-log canonical singularities, SLC for short. And I'm not going to give you the definition, but possibly you already know it, but I want to describe how you construct concretely examples of stable surfaces. So if you want for a stable surface, then of course you can the list of semi-log canonical singularities is sort of restricted. You can have canonical singularities like rational double points. You don't really even consider these as singularities because they are divisible in the least moduli space. Then there are quotients of the affine plane by a finite linear subgroup, simple elliptic singularities or cusps. These are Gorenstein. And then there are some quotients. These are classified. I don't want to give all the details of this simple elliptic and cusps. And then if you want to construct a stable surface, you may start with a smooth surface and with some configuration of curves that can be blow down the configuration. And then of course you have to fulfill the, of course you start with some configuration that leads to one of the admissible singularities I've listed. And then you need to check that KX is ample. And to do this, you just look at the pullback and you have to check that this is not, and that the only curves that have zero intersection with the pullback of the canonical class are the exceptional curves. And I'll give you an instance of this contraction later. But let me go to the non-normal case. Then, what do semi-log canonical singularities look like in the non-normal case? In dimension one, you have what is called double crossings, the analog of the singularities you get in the curves, like Rollenske crossing. And there are finite number of worse singularities. And to the condition that the surface has SLT singularities can be read on the normalization. So you take X, look at the normalization, then you have the locus, the closure of the locus where you have double crossings points. So there is a curve where the surface self-intersects. And we call this D, and we look at the pre-image. This is sort of naive. It's actually these are the schemes defined by the conductor. And so this is normalization, and the map from D bar to D is 2 to 1. So you don't have an involution associated with this map because D bar is singular in general. But if you go to the normalization, let's call it D bar D, then you have actually an involution on the normalization of D bar. And this involution has some geometric property, it preserves the different. I'm not going to define the different, but it's a Q divisor, an effective Q divisor on D bar nu that is the correction term in order to make the adjunction formula work in this singular situation. And so from a non-normal stable surface, I produce a pair with X bar normal divided by effective divisor and an involution. And the pair has log canonical singularities and the relative canonical class KX bar plus D bar is ample. And Pollar's construction tells you you can go backwards. So you start with such a pair, stable, meaning as usual that KSBA is the bar example, and involution preserving the different. And there's some gluing procedure that produces a stable surface. And let me give an example that will reappear later. So here we start with P2, take a line, and then general quintic, I'm sorry, it's very loud. A general quintic curve. So this is some is the static. So you can take the double cover of P2 branched on this curve in red. And this is basically catering. It's slightly singular. You will have A1 points nodes at the over the points where the line intersects the quintic. I call D1 the pre-image of this line. I don't know if you can read it, but the name of the line is L1. And since this is in the branch divisor, it is a P. D1 is isomorphic to L1, it's a P1. And I do the same thing twice and produce a second surface with the same properties. And then as soon the difference here is 1/2 the sum of the PIs. And of course, the same is true for the second surface. So if I want to apply Collar's construction, it is enough to find an isomorphism between these the pre-images of this line and this line that maps the P1, P5 to P1, P5. And of course, you can arrange things in order that this is possible. It's not possible in general, but and this gives, so we have all the conditions. We can glue the two surfaces together and we get a stable surface. Of course, there's, sorry. In both cases, K is trivial. P1 is numerically 1/2 pullback of a line, so it's ample. So this condition is satisfied. Singularities are of the type required, and so you have a stable surface, and you can compute the invariance. Just you have to believe me here. I'm not going to do it in public, but we get k² = 1, and H2 of O is 2, H1 of O is 0. And one interesting feature of this example is that this is dual to H0 of Kx. So the canonical system is a pencil at dimension 1, but the canonical curves are all supported on this intersection curve. They are all rho reduced and with the same support. So, these constructions are not so hard to perform, at least in some cases. The problem is to know where the surface you have constructed lies in the Moduli space. Usually you want to know if it's in the closure of the main component. If it's a limit of smooth surface, or it lives somewhere else. And that's the harder part in this kind of analysis. So let me tell you what the ice surfaces are. It's the example we have been analyzing for a long time now. So a nice surface is a stable surface exactly with the same invariant as the example I just constructed. So it has k² = 1, the geometric genus PG, which can also be defined as H2 of X. Again, I forgot to write something. So geometric genus is 2, the irregularity which is h1 over x is 0. And when I say classical eye surface, I mean a surface with these invariants, but with at most canonical similarities, smooth or canonical similarity. And why these surfaces? From the point of view of people who work on surfaces, they are good because they are a square is always positive, so 1 is as small as possible. One advantage of this choice, for instance, is that the Rollenske examples are all irreducible, because k square is the sum of k square of all the components, and if we have integers adding up to 1, but I have only 1. And this is on the one of the Yorikawa lines. What I mean is that there is a meta inequality that gives you a lower bound for k square in terms of the geometric genus. Is k square greater or equal than 2pg minus 4. So this is the pg is the biggest possible, pg equals 2 is the biggest possible for k square equal 1. And experience tells us that the closer you are to the neutral line, the easiest is to understand the surface. So that's all. At least we know what the classical ice surfaces look like. And there's also, I try to relate to the theme of the conference, that's also no Hodge theoretic size. And it's somehow the smallest possible example with PG greater than 1. And this has been used as a test by Green, Griffiths, Lazar, Robles, that have an ongoing program in extending at the same time, I think, choosing a suitable desingularization of the modular, of the physical modular space in order to be able to extend the period map to this compactification. And we have something more about this will be said in Marco Franciosi's talk tomorrow. And just to, like, fun fact, these surfaces are simple, but it's not known whether global Torelli or generic global Torelli holds for these surfaces. There's a paper by Erstein and Zhang in 2017 where they proved global generic Torelli, but for a special subfamily, which has a bigger automorphism group. So let me tell you what I don't know, get rid of this whistle. I'm sorry. Okay, let me tell you what eye surfaces look like. So the canonical map is not very useful because it's bad, so you see a federation of the one, but you can look at the bicanonical map. And then bicanonical map is 2 to 1 on the quadratic cone in P3. Because I think this was conceived for a man's shirt, whereas buttons on the other side. That's why now that stopped whistling apparently. Okay, so I was saying, so the bicanonical map realizes these surfaces as a double cover of the cone. I drew a picture here, and this double cover is branched on the vertex, which I call O, and on the section with a quintityper surface in P3. And in order to have canonical singularities for X, the branch locus must be either smooth or have so-called single singularity, AB singularities. And you can easily count parameters, and you find that you have the construction depends on 28 moduli, and M13, which is the moduli space of classical eye surfaces, is irreducible, reduced, actually it's rational. And this construction gives us also useful information about smoothing, because all these surfaces, all these classical High surfaces have an involution that acts as the identity both on the canonical and bicanonical system. And so if you have a stable surface, which is the limit of classical ones, of smooth ones, then it has an involution with the same properties. So if you can show that there is no involution of this type, then you know that the surface is certainly not smooth. And I'll show you examples of this. So now the question is trying to understand what lies at the boundary. And the most simple-minded thing you can do, I think, is just, let the branch locus acquire worse singularities. And by basically the Urbis formula, the surface will stay similar canonical as long as the pair given by the project cone and half the branch divisor is similar canonical. So this gives you, if you degenerate B, but avoiding the vertex, such a way that B does not meet the vertex. And one has, this is a log canonical pair, then you get a Gorenstein stabilized surface, which is of course smoothable because you describe it by specializing. And what we proved with Franciosi and Rollenske, have this ambiguity here. This is raw and not rough. All Gorenstein surfaces arise this way. So for the Gorenstein examples, this is somehow understood what they are. And sorry. I don't know what happened. Okay. So as long as the branch locus is reduced, you have normal examples. And if you let the branch locus become non-reduced, then you get non-normal surfaces. And I have here a beautiful table that I copied because I'm not good at making table that where we stratify this Gorenstein, the open set of Gorenstein surfaces according to the type of singularities. So you have a main stratum corresponding to the smooth smooth surfaces, and then let me try to explain what the notation is. This is N stands for normal, and then you can have the Gorenstein singularities that are not canonical are simple elliptic or cusps. And in this case, we can show that you can only have degree 2 or degree 1. So this means normal with a degree 2 elliptic singularity, and one is normal with a degree 1. And then, of course, you have combinations like N1, 2, for instance, means a normal surface with 1 degree 1 elliptic singularity and the degree 2, and so on. And in the last part, we have the non-normal ones. So this is, and they are classified according to the type of the normalization. So you have the pezzo or P2 or a minimal ruled surface ruled over an elliptic term. As you see, we have listed here the type of the minimal resolution and the codial dimension. And another reason why it's easier to study these examples is that since k² equal 1, the normalization or the minimal resolution of the stable non-classical surfaces are never of general type. So you have to deal with surfaces that say And what one might not like in this picture is, you see, we have the dimension of the strata here. And the biggest one has already the dimension 8. So one would like to know devices in the boundary. So in this case, all the strata have very high codimension. I have here a picture with the possible degeneration. Again, this is the smooth case, and you can degenerate to one elliptic singularity of degree 1 or 2, and they have a common degeneration to 1 and 2. And so you can read this for yourself. Let me just stress 2 points. There is this interesting thing that for other combination of elliptic singularities, you know what the, if you look here, you know what the minimal resolution is. For this type, 2 elliptic singularities of degree 1, you have 2 possibilities that either the minimal resolution is rational or it is unrequest. That's why R and E. And then also, not all possible combinations of 3 elliptic singularities actually occur. And there is a not theoretic counterpart. Actually, you need a finer stratification where you distinguish between the simple elliptic and cusp singularities. And Mark is going to explain that tomorrow. So far so good for the Doriston case that one would like to see further degenerations. So again, possibly the most simple-minded thing you can do, just let the branch locus go through the vertex. In this case, the surface is not Doriston anymore. Still it is 2 Doriston. If you just take degenerate through the vertex, you get a singularity of type 1,4,1,1. And then you can try more complicated things. The most, I think, the most degenerate you can get is described here. You can take the quintic surface to be everywhere tangent to the cone. So the branch locus is twice a veil divisor. And when you normalize the double cover splits, it's 2 copies of the cone through the long this curve. Another possibility is instead of degenerating the branch locus, is to degenerate the cone. And since the cone is naturally embedded in P3, you can degenerate it to the union of 2 lines. And if you take the double cover of this, I tried to draw a general degeneration. Again, you see, this is the intersection with the quintic section. So I get quintic section of the pair of planes, so quintic on each plane, and then there's the line where the 2 planes meet. And if you take a double cover branch on this, we recover our K3 plus K3 example, the one that I gave to show you how collapse construction works. So in this case, we see that that example that we constructed in abstract is actually movable. Another possible strategy, which has been used by Gallardo, Kirsten, Schaffler, and Jean in a paper in 2022, is to let the acquired singularities that are worse than semi-level canonical. Then the double cover is not a stable surface, but you can perform a semi-stable reduction and replace it with a suitable stable surface. And they did a very detailed, a very interesting job. They chose 8 unimodular singularities that are not semi-log canonical, and for each of them they studied the semi-stable reduction. And this way they get 8 divisors in the modular space. And the general surface in each divisor is a kind of generalization of our K3 plus K3 example. Is the union along the P1 of basically K3 with canonical singularities, and another surface that has the same numerical invariance as the K3, so PG equals 1, Q equals 0, but may have worse singularities. And I think these are not so interesting, not theoretically, because they are somehow the analog of compact type curve. You have the H2 is still a pure structure. We at this point we try to choose a different approach, and because as I said, this is somehow the easiest case, but as I told you, you have a modular space of dimension 28, so not so easy to explore. So we decided we would like to look for divisors, and so we looked at the so-called P-singularities. These appear in the classification of normal semi-log canonical singularities. And these are quotient singularities of a certain type. 1 over m squared d, 1 and dA minus 1. I guess you know the type of notation. This means that the cyclic root of this order x, then you fix a primitive root of that order, and you have a diagonal action with z to the 1 and z2. This is the exponent of the second eigenvalue. Why these singularities? Because these are the only quotient singularities, apart from canonical singularities, that locally admit the covariance smoothing. So, of course, if you are interested in smoothable surfaces, at least you better start with something that is at least locally smooth. And these numbers that appear in the definition have a geometric meaning. M is the Cartier index, like the smallest integer, such that M times the canonical class is Cartier. And D is the expected dimension of surfaces with this type of singularities inside the modular space. It's the dimension of the cubic component of the local deformation of the singularities corresponding to covariance smoothings. And these come in families. If you increase D by 1, and then the singularities with the invariance and the A specializes to the and D plus 1A. So you go one step further inside the stratum. So this means that for D equal 1, you expect the divisor. And just for simplicity, we call this singular surface is a stable surface that has one singularity and is moved elsewhere. And we try to understand what are the possible singular I-surfaces. And this is work with Franciosi, Rana, Rollenske in 2022. And in fact, the list is not very long, as you can see. Cartier index 2, you have several possibilities for D. This, I think, it's not sharp, but anyway, it's a bound. Then there is one possibility for index 3 and one possibility for index 5. Let me remark that this is not what you expect into dimension 1. By what I said, this is a codimension 2, extracted in codimension 2, and it's a specialization of 1 over 9, 1, 5, and then you can see 1 over 9, 1, 5 is not in the list, so that does not appear. And so let me tell you what these surfaces look like. these are the possibilities, and all possibilities are actually realized. So for m equals 2, this is just something we have discussed. 1, 4, 1, 1, you will get by letting the branch locus of the double cover go to the vertex in a generic way. If you make it more tangent or more singular, then you get singularities in the same series, but with higher D. For m, I'm not going to explain you what m equal 3 looks like, because structure is similar to m equal 5, but I think m equals 5 is more interesting. You see why. So first, we want to construct a nice surface with a singularity of type 1 over 25, 1 to 14. And so we have to look, as I explained, one possible way is to find a smooth surface with a certain configuration of rational curves that you can blow down to this singularity. And to know what such a configuration looks like, it's not hard. It's a string of P1s, and with the self-intersection of P1s are given by expanding 25 over 14 as a continuous fraction. So you get 2, 5, 3. So the exceptional divisor is a chain of 3 rational, smooth rational curves with self-intersection -2, -5, and -3. And so how do you find something like this, let's say in nature? So you start with a properly elliptic surface with Pg equals 2, Q equals 0, and with a -3 section. This will be 1, this self-intersection -3. And then you look at the singular fiber. In this picture, I have another cubic. So you blow up here, and you create a -1 curve. It's not in the picture, but you create a -1 curve intersecting twice the blow up of this. And then you blow up at one of the 2 intersection points, as shown here. So here we have the -5 curve is the strict transform of the singular fiber. The -3 curve is the section that was already there. And the strict transform of the first sectional curves gives you the -2 curve. If you contract this configuration, you'll actually get a T-singular surface with the invariance we are looking for. And of course, you can do some kind of variation, which is instead of considering another elliptic curve, you take a KSBA. And in this case, when you at the first blow up, you get the exceptional curve, and the strict transform of the fiber now is tangent instead of meeting at 2 points. So you have no choice. You blow up this point and get a similar configuration. And we can show that all the surfaces are desingularized surfaces with this type of singularities arrive like that. Of course, that leaves us with the question whether they are smoothable or not. And I'm not going to go into the details, but the general case is not smooth because of there is no involution. And this is due to the fact that there is an asymmetry in the construction. Once you blow up, then you decide for the second blow up, you choose arbitrarily one of the 2 points where corresponding to the 2 tangents. And it's not hard to see that this makes it impossible to have an involution as we wanted. This does not happen for the second case, the KSBA case, where the strict transform meets the exceptional curve at 1 point, so you have no choice. The blow up is canonical. And also, if you count moduli, you'll see that this construction has 28 moduli, since our space has, I mentioned, 28 cannot be in the closure. But this remark I made gives you a more precise picture of what is or may or may not be smoothable. So we have this conjectural picture of what the part of the boundary of M13 corresponding to T singular surfaces look like. So we have the main component where the smooth surfaces live. We have another component of the same dimension with these 1/25, 1/14 surfaces are. And conjecturally, the cuspidal ones are in the intersection of the components, namely they can be smoothed. And the remarkable thing about this 118.15 is that it is expected in codimension 1, but actually it happens, it is expected in codimension 2, but it actually happens in codimension 1. And these are also, as the picture shows, they are smoothable. Of course, the picture smoothability is not a very simple thing to. We did it directly. You write down the canonical ring of these surfaces and then show that it can be smoothed out. But it's far from trivial. I can say it because I'm not the one who uses the canonical rings. So. Okay, and so, we went on with this story, trying to make this conjectural picture less conjectural. And so we added Stephen Coughlan to our team, which is a really valuable addition. Okay, we have this much more precise picture. So you see, again, this is the component corresponding to the smooth surfaces. This corresponds to the singular surfaces of the index 5. I forgot to tell you, RU stands for Rana because the first examples as in the literature of this surface is in a paper by Rana. And so what we did, we showed that the conjecture was true, like the Rana surfaces arising from the cuspidal construction are smoothable. And then we looked at tried to understand how the different strata are connected. So as you see, for instance, here, it's a codimension 2 stratum corresponding to surfaces with one singularity 1/4, 1/1 and 118.15. On the other hand, the other combination, the 1/4, 1/1 plus 1/25, 1/14, we showed cannot happen. And here, in this component corresponds to 1/25, 1/14, we can also find this singularity that did not occur alone. And when you go to the intersection of the two components, this becomes the singularity we had already met, 118.15, which is the specialization of this surface. And as to the methods, we mix different techniques. Sometimes we look at the singularization and so work on a smooth surface and study this configuration of curves. But again, the smoothability instead is done by writing down the canonical rings. And I think this is especially nice in the case of MRU, the case of these surfaces, because there's a uniform description in this component and there's a parameter. And when that parameter is 0, then you are here, and the canonical ring can be put in a different format and can be smoothed out, and what is not possible for the rest. And I think we are a bit tired of looking at this surface. That's taken up a long time, but still we are some work in progress trying to describe the two garnishing ice surfaces. So the ice surfaces such as 2K axis Cartier, that the further detail I refer to Marco's talk. So I think I might be early, but I hope you don't mind.
Yes, thank you.